Hey guys, this is problem 3. Problem 3 is an interesting problem, and there's probably a few different ways of doing this. You can actually get a few different solutions, and as long as your solution makes sense, then you can use it, and we'll grade accordingly. This really tests to see how well you not only understand how to draw moment and shear diagrams, but how well you actually, let me zoom out a little, how well you actually understand them, not just drawing them, but how they work. So I'll just give you a few things that you should look at right away. Right here, you have a jump in shear, so you know that you have to have either a reaction or a point load. Here you also have a jump, so you should also end at here you have jumps. Here, here, and here you have jumps. This is a smooth drop, so it's not a jump. But here, here, and here you should have point loads of some kind. They can be in the form of point loads, they can be in the form of reactions. It's really up to you, but they need to be there. For this one, remember that you normally end at a with the 0, 0 moment. This doesn't matter if you have a simply supported beam, if you have a free end beam, like your moments at the end are usually 0. So the fact that this is non-zero means that you must have a moment at the end. And there are a few different ways you can do this. For example, you can use an applied moment. You can say that there's an applied moment M. There's some applied moment at the end, and then use draw this however you want. The other way of saying it is that the end is cantilevered, and it's like this. But yeah, there's a few different ways of doing this. Remember that you probably want to keep your structure. Yeah, so the instructions even tell you that your structure has to be determinate. So you really want to pay attention to the number of unknowns you're having. You can have, if you have a cantilever like this, you cannot have any other forces. You cannot have any other reactions. So you'll need to get cute with your locations of your forces. But yeah, then the other thing to keep in mind is that so this is decaying here, and the slope of this is equal to your distributed load. So your slope of this is your distributed load, so the slope of this line is 0. So this tells you here that you should have a distributed load. This here tells you that you should have your distributed load ends. So between here and here you have a distributed load. But here you have a jump, and this distance here is 10 kilonewtons. It's 5 plus 5. What these 10s are actually showing you is the length of this member. So this is 5 here. This is 5 here. It's not saying that this is 5 and this is 5. I don't want to hear like this is, oh, was this negative or positive? It's just showing you what this length here is. Yeah, and then once you have your reactions, this 50 kilonewton is what's going to throw a lot of people off. I think the fact that it's not 0 at the ends, but yeah, just remember how you the things you can do. You can use a cantilever, you can use an applied moment. Yeah, just keep those things in mind. Yeah, I'm not sure really what else to say for this problem, so let us know if you have any questions. Do make sure you're comfortable deriving your beam. Oh yeah, this has to be a determinant beam. I think I said that earlier, but it has to be a determinant beam. But if you understand how to do this and understand how to do number 2, then you should. I don't really see how you can do poorly on the final or on the quiz. Yeah, so yeah, because these things will be extremely important. Yeah, anyway, let us know if you have any questions.